This is lesson 2 from chapter 5, and please open your books to page 357. And this is the first time I've asked you to watch a video for homework, so it's important that as I show anything in the book that you pause the video and you write exactly what I've got written, or you do the problems that I ask you to do, because I will check that first thing tomorrow before you can move on to the next activity. So for tonight's homework, we're going to go over lesson 2 called sequences. And just follow with me in the vocabulary startup. A sequence is an ordered list of numbers. Ordered just means that there's a first element, a second element, a third element. So a sequence is an ordered list of numbers. Each number in a sequence is called a term. So term number 1 is the very first element in the sequence. Term 2, term 3, and so forth. An arithmetic sequence is a special sequence that's found if you add or subtract the same number from the previous term. So arithmetic sequence, and I always think about the word arithmetic, and it reminds me of an old-fashioned word for math. If you remember ever watching Little House on the Prairie or any early colonial time shows, when they have a one-room schoolhouse, they won't say, "It's time for math class." They'll say, "It's time for arithmetic." So arithmetic is kind of the most basic old school math, and if you can relate that word to the idea of adding and subtracting, that will help you remember that an arithmetic sequence is when you are adding the same number every time or subtracting. So to continue each sequence here, notice 1, 3, 5, 7. You want to ask yourself, how much is continually being added? Well, notice that we are just going to be adding 2 every time. So the next term here would be 9. This next one, take a look and try to figure out what you would add each time. And we'll fill in the sequence. So 1 to 1.5, we're adding 0.5. 1.5 to 2, we're adding a half. So as we continually add halves, it's going to look like this. So if we're asked to put this into words to describe each sequence, we would add 2 to the previous term. And for this one, we would add 1/2 to the previous term. I'm just going to draw an arrow so that that means the same thing. So that's the basic definition of an arithmetic sequence. Let's take a look at the real world link. The number of students who went on each horseback riding trip is shown. Do the numbers represent the terms of an arithmetic sequence? So when we're talking about the sequence, we're not talking about this top row. This top row is kind of just like our counter. Trip 1, trip 2, trip 3. It's just kind of keeping our numbers in an order, like term 1, term 2, term 3, term 4. Down here, this is the actual sequence that we're talking about. So the question is, do these represent an arithmetic sequence? So in order to determine if it's arithmetic, we have to decide, are we adding the same number every time? Well, one of the notations I use a lot is with these arrows, and I would say from 15 to 16 I'm adding 1. From 16 to 18 I'm adding 2. 18 to 21 I'm adding 3, and then I'm adding 4. So are we adding the same number every time? No, we are not. We are adding continually 1 more each time. So we would say this is not an arithmetic sequence. It still can be called a sequence of numbers, but it doesn't fall into the category of arithmetic. Okay, please turn the page and take a minute to look at example 1. So they're going to ask you to describe the relationship between the terms. So notice they use that same kind of arrow notation I do. So to describe it, you would say that we are continually adding 5 each time. And then it's going to ask you to continue to find the next 3 terms. So you're going to have to add 5 3 more times to get those next 3 terms. In example 2, notice that what you add each time doesn't necessarily have to be an integer. It could be a decimal number. So here we're adding 2/10 every time. Okay. So I would like you to pause the video and complete A, B, C, and D. Make sure that you describe the relationship. So if you wanted a shortcut way to describe this, if I were doing this, I would say, okay, from 0 to 13, we're adding 13. From 13 to 26, we're adding 13. And from 26 for 39, we're adding 13. So to describe the sequence, if you just want to real quickly say we are adding 13, that would be a way to describe it. But now you need to find the next 3 terms. So 39 plus 13 is 42. Plus 13 is 55. And plus 13 is 68. So that's what you need to do for B, C, and D. Pause the video, and when that's completed, you can start the video again. Okay, I will check B, C, and D first thing tomorrow to make sure that those are complete. So now let's go to the top of page 359. And we want to now take a sequence and we want to try to write an algebraic expression. In other words, we want to find a connection between the term number and the term. So this is the first term and it equals 2. The second term equals 4. The third term equals 6. And the fourth term equals 8. So we want to see, is there a connection between the position and the value of the term? So mathematically, do you see a pattern that's happening? What do you do to this top number to get the bottom number? And is it the same? Okay, so hopefully you can see that if you take this number at the top and if you double it, you get the term value. So the first term is 2, second term is 4, third term is 6, and so forth. So we want to go all the way out here and we want to say, what if we had the nth term? And we're going to put the variable n, meaning any position. What would you do to this number to get the term value? Well, we would double it. So 2 times n is how you would represent what's happening here. So for any position, you just double it. So 4 doubles to 8. 5 would double to 10. 6 would double to 12. 7 would double to 14. All the way out, and that would work for any value here, n, you would just double it. So that's what we want to try to do. We want to try to come up with this expression. So notice that down here they did this in the same way, but with a table. So position 1 was 2. Position 2 was 4. 3 was 6. 4 was 8. And they tried to get you to see that we're just doubling. So please circle this. Here's the overall expression for any term. The value of the expression is 2n. So example 3. The greeting cards that Meredith makes are sold in boxes at a gift store. The first week, the store sold 5 boxes. Each week, the store sells 5 more boxes. The pattern continues. What algebraic expression can be used to find the total number of boxes sold at the end of the 100th week? Well, when you start to look at this pattern, week 1, position 1 was 5. Week 2 was 10. Week 3 was 15. So we want you to start to see an operational connection between the position and the value. So if you notice that all we're doing is we're taking the week number and we're multiplying it by 5. So in that case, after the 100th week, we would simply be finding 5 times 100. So the 100th week is when n is 100. 5 times 100 is 500. So at the end of 100 weeks, 500 boxes will be sold. Okay, please turn the page. The got it question at the top. Sometimes your sequence will be represented as a figure. So the best way to do that is to try to turn that figure into a numeric value. So do you see that figure 1 has 3 boxes or circles, then 6, and then 9? So you want to recognize, first of all, that this is arithmetic. We're adding 3 every time. And now we want to make a connection between the figure number and its value. So what's the connection between 1 and 3, 2 and 6, 3 and 9? And we want it to be the same. So what are we doing to each of these numbers to produce this output? So hopefully you're seeing that we're tripling it. So way out here, figure n would just be 3n. So how many circles would be in the 50th figure? It would just be 3 times 50, or 150. Okay. What I'd like you to do right now is complete these 4 questions in guided practice. Make sure you're showing your work, and then you will be done with your assignment. Have a good night.